So this unit 4 is based on deep learning and convolution neural networks. Okay, so this unit 4 is based on deep learning and convolution neural networks. So in today's lecture, we are going to have introduction to deep learning. So under this unit, we will be studying about what is deep neural network, what are certain issues related to deep neural network like vanishing gradient, overfitting, computational load and activation functions. Then what do you mean by dropout architecture in case of CNN? And what is architecture of convolution neural networks? Okay, and then we will have look at some applications of CNN. So in today's lecture, we will try to go through these topics. So what is deep learning? Then why we need deep learning? Then about certain problems like vanishing gradient, overfitting, computational load. And then we will have look at what is ReLU activation function. So basically, what are various challenges in machine learning? Why we go for multi-layer perceptron? Can anybody answer? Why we cannot use only single layer perceptron and why we go for multi-layer perceptron? Now we have talked this many times in previous lecture. So please answer this question. Why we go for multi-layer perceptron? Please type your answer. Please type your answer. Why do we need multi-layer perceptron? We talked about this many times when we started with multi-layer networks, neural networks. So there is one answer that images are in high dimensions. So that is not correct answer. So one more answer is it can represent most logic well. For example, XOR gate cannot be represented using single layer perceptron. Yes, Subhasmita, this answer is correct. So basically, in case of neural networks, if in case of your input data, if input data is not linearly separable, we cannot perform classification by a single layer perceptron. So yes, Saloni, your answer is correct. For non-linearly separable data, we need multi-layer perceptron. Okay, so basically when your input data is it cannot be separated by a single line or a single surface or linear surface. We need to go for multi-layer perceptron. Now, when we go for multi-layer perceptrons, there are various issues like network structure becomes complex. Similarly, computational complexity increases. Then it is required to change its internal presentations or generate a feature vector. So from the raw data, it is necessary to generate feature vectors. Then working with these features is required. So more engineering is required before applying that data to actual network. You need to extract certain features. Then you, if there are large number of features, you also need to apply some dimensionality reduction technique, or you need to decide upon which are important features. So you need lots of pre-processing on the data. Then algorithms need to be guided about what kind of function they should learn. So we should guide the algorithm properly. And then we usually use back propagation algorithm. So whether the gradient is appropriate, whether if gradient becomes too small, there are other problems like your weights won't be updated properly. Okay, so these are various challenges when we go for multi-layer perceptron. Okay. So we usually we go for deep learning when we want to avoid certain problems. So deep learning is a machine learning technique that teaches computers to what comes naturally to humans. So basically we focus on learning by examples. Okay, so in case of deep learning, as compared to your conventional neural network, more number of hidden layers are used. So that's why the name is deep. Deep because there are many number of layers in the network. Okay. So deep learning is a subfield of machine learning concerned with algorithms inspired by the structure and function of the brain. Okay. So this is basically a special branch of artificial neural networks, and this we can say as final product of machine learning. So learning rule becomes the algorithm that generates the model, and uh, it generates the model from the training data itself. So in case of deep learning, what is important is we should have ample amount of examples. Okay, then only we can go for deep learning, and your deep learning trained network will give you desired performance if you have sufficient amount of training samples. Okay? So basically, we go for deep learning because it gives you better optimization methods. It gives you faster convergence and better accuracies if we use appropriate techniques. Okay, so these are certain deep neural networks. Then with deep learning, we need to use some different type of activation functions. So initially we started with logistic function, or we use simple threshold function or step function. Then around in 1991-92, we started using sigmoidal function or Banach function. And after 2010, the other few other activation functions were introduced, like ReLU, then parametric ReLU, etc. So for convolution neural networks, which is an example of deep neural network, usually ReLU or leaky ReLU activation function is preferred over other activation functions. Then with deep learning for better regularization, we can go for dropout architecture, and we can use batch normalization techniques. Okay. So as shown in this graph, as amount of data increases, your deep neural network gives better and better performance. Greater the amount of data for training, we get better performance. Whereas with old neural networks or conventional neural networks, where number of hidden layers was limited up to 4 to 5. So for those, though after certain stage, though you increase amount of data, it doesn't give better performance. Okay, whereas with deep neural networks, as you keep on increasing amount of data, you get better and better performance. So let us have a look at what is difference between your conventional neural networks and deep neural networks. So in traditional machine learning algorithms, we use some feature extractor, and then we use a classifier. Okay, then in mainstream modern pattern recognition network, that is which comes under unsupervised learning, we use some feature extractor module, then we have some mid-level features, and then classifier unit. And when we say deep learning, in case of deep learning, your feature extractor is part of the network. Okay, so feature extractor, mid-level feature extraction, high-level feature extraction, all these three are part of your neural network. So your neural network performs feature extraction and mid-level and high-level features extraction as well as classification on its own. So with conventional neural networks, we need feature extraction as a separate unit, and then we apply those features to the neural network based classifier. Whereas in case of deep learning techniques or convolution neural networks, first few layers are used as feature extractor, and then last few layers they perform classification job. Okay. So this is about timeline for general neural networks to deep neural networks. So your basic neural network approach, it was proposed in 1940s. Then in 1960s, number of layers in the neural network were increased and concept of deep neural network was introduced. Then in 1989, very first deep neural network architecture was available. It was for recognizing digits and the network architecture name is LeanNet. Okay. Then in 1990s, hardware for shallow neural networks were available by Intel, ETANN. Okay, so in 2011, some speech recognition deep neural networks were introduced by Microsoft. Then in 2012, DNN, deep neural networks, basically for vision application, they were developed, and this one of the example for vision based deep neural network is AlexNet. Then in 2014 or onwards, there was lots of research in DNN, and it has accelerated this vision applications as well as speech application, and many new architectures were available like new flow, Now, etc. Many other architectures for vision applications are available after 2014. So there is one visual recognition challenge known as ImageNet. So this ImageNet is a large-scale visual recognition challenge. So the ImageNet large-scale visual recognition challenge, it evaluates algorithms for object detection and image classification at large scale. One high-level motivation is to allow researchers to compare progress in detection across a wide variety of objects and taking advantage of the quite expensive labeling effort. So this ImageNet challenge provides you labeled data, which is huge in number, and it consists of various types of objects. And you can participate in this challenge and you can develop your own deep neural network architecture for classification and detection of objects. Another motivation behind this ImageNet challenge is to measure the progress of computer vision for large scale image indexing, for retrieval and annotation. For details about each challenge, you can refer to the link. So you can go through this link, and this ImageNet challenge is given by, this is developed by Stanford Vision Lab, Stanford University, Princeton University. So you can go through this link, or you can type for ImageNet challenge, you will find this link, and you can also participate in this challenge for detection of objects. So this large scale visual recognition challenge, so initially in 2010-11, shallow networks were used for detection of objects. Then in 12, there were 8 layers. Even in 13, 8 layers neural network was used, and the network architecture was known as ZFnet. Then in 2014, this challenge has used almost 19 layers, and the network was known as VGG network. Then in 2014, Google Net was used where there were 22 layers. And after that, every year number of layers were increased. And in today's era, you can have more than 152 layers. So one of the example is ResNet, which uses very large number of deep neural layers. Okay. So there are various applications where we can make use of deep learning techniques. So DNNs are widely used in multimedia applications like computer vision, speech recognition. It is used for many applications for image and video analysis. It is also it is also useful for speech recognition and natural language processing applications. It is also useful in medical domain for detecting abnormalities in MRI images or ultrasound images or X-ray images. It is also useful for computer game development. It is used in robotics domain. It is also useful for finance applications like trading, energy forecasting, and risk assessment. It is useful for infrastructures like structural safety, traffic control, and it is very useful in earth resource related applications or weather forecasting and event detection applications. So in video is arguably the biggest of the big data. So it accounts for over 70% of today's internet traffic. We can easily transmit and receive videos. So there are many applications with deep learning where you can process the video. So over 800 million hours of video is collected daily by worldwide video surveillance systems. Computer vision is necessary to extract meaningful information from these videos for various applications like surveillance applications. And DNNs have significantly improved the accuracy of many computer vision tasks. So these tasks include image classification, object localization and detection, image segmentation, then action recognition or anomaly detection, then scene classification and scene parsing, image captioning, video summarization, then generating authentic photos. So you can generate the authentic photos by using GAN networks or generative adversarial network. Then generating images, again this is application of GAN network. Then under speech and language, you can have various applications of DNN. So with DNN, we can significantly improve the accuracy. And this accuracy improvement is possible with tasks like machine translation, natural language processing, audio generation, and also for question answering, like for developing applications like Alexa, you can actually, it works on DNN networks. Okay. Also, this deep learning has played important applications under medical domain. So DNNs have played an important role in genomics to gain insight into genetics of diseases such as autism, cancers, then spinal muscular atrophy, etc. They have also been used in medical imaging to detect skin cancer, brain cancer, breast cancer. Then it also has applications in game. So recently, many of the grand AI challenges involving gameplay have been overcome using DNN. These successes also required innovations in training techniques, and many rely on reinforcement learning. Basically, for gaming, your specific action depends on many previous actions. So that's why here reinforcement learning is used. DNNs have suppressed human level accuracy in playing. Then few examples are Atari or Go, where an exhaustive search of all possibilities is not feasible due to unimaginable huge number of possible moves. So in such cases, your deep learning techniques can work well. Under robotics, again, deep learning techniques are very useful. So you can have robotic applications such as grasping with robotic arm, motion planning for ground robots, visual navigation, control to stabilize a quadcopter, and driving strategies for autonomous vehicles. So now let us have a look at what are certain issues or challenges when we are using deep learning. So basically, when we say deep learning, there are multiple layers in the neural network. So because of that, we may face certain issues like vanishing gradient or overfitting of the network. Then computational load is very huge and non-robustness. Okay. So are there any solutions to these challenges? Yes, of course, there are solutions. So before going to solutions, let us understand what do you mean by these problems? Okay. So all of us, we know what is a basic perceptron. Okay, so this is basic perceptron which makes use of step function. Okay, so here output is 1 if your aggregate or net output becomes greater than 0, and output is -1 or 0 otherwise. Then we also studied sigmoidal activation function. So this we on the net output we apply this sigmoidal activation function 1 upon 1 plus e raised to minus net. Now when we go for multi-layer perceptrons, we make use of back propagation algorithm. So uh, please tell me, in case of back propagation algorithm, weight updation is proportional to which parameter? So please type your answer in the chat box. Weight updation is proportional to which parameter in case of back propagation algorithm? How we derive the change in weight? Change in weight is proportional to which parameter in case of back propagation algorithm? Yes, error function, but whether we use that error function directly, Vedika or all other students, of course it is your weight updation is proportional to error signal, but whether it is directly proportional to error signal or we apply some mathematical function on it, we consider some mathematical operation. What is that operation? Error, alpha, and final output. But what mathematical operation we apply on the error signal? Yes, derivative term. Yes, Vedika, very good. So basically, we consider derivative of error signal with respect to all weight values, and we propagate it by backwards from output layer to first hidden layer, then first hidden layer to next hidden layer, and then to input layer. And according to this derivative value, we keep on updating the weights. So in back propagation algorithm, basically there are 3 phases. First, we propagate the signal forward. Okay, so we determine the net output, we apply activation function, and we follow similar process at each and every layer. Then we calculate the error. Then we determine derivative of the error and we propagate it backwards. So in back propagation, what we do is we adjust the weights of neural network in order to minimize the network total squared error. So we change all the weights so that overall error is minimized. So because of this process, backward propagation of gradient, we come across a problem known as vanishing gradient. So when we move from, say, this output layer to first hidden layer, then first hidden layer to next layer, and so on, when we come closer to hidden layers which are near to input layer, there is possibility that gradient value becomes 0. And the same is known as gradient vanishes. When it becomes 0, it is known as it vanishes. And when the gradient vanishes, when gradient becomes 0, your del W becomes 0. So for the layers which are closer to input layer, there won't be any weight updation because your change in weight is directly proportional to the derivative or gradient. So if your gradient becomes 0, there won't be any weight updation at these layers which are closer to your input layer. Okay. So this problem is known as vanishing gradient, and it takes place in deep neural network because there are many layers. Okay. And there are some other reasons. Okay, so vanishing gradient occurs in a training process of back propagation when output error fails to reach the farther node. So when your gradient becomes 0, it is not possible to reach to farther layers, farther from the output layer, and hidden layers close to the input layer are not properly trained. Because if gradient becomes 0, there is no weight updation, means those layers are not at all trained. Okay. So weight update rule in case of back propagation algorithm is W new is W old plus del W, and del W is always proportional to gradient of error. So if gradient is 0, weights are not at all updated, and thus hidden layers close to the input layer are not properly trained. Okay. So now let us see why the gradient vanishes. Okay. So we know that this is your sigmoidal function. So the sigmoidal function compresses all its inputs to a range between 0 to 1. Okay. So a sigmoidal neuron is said to be saturated when sigma x is 0 or sigma x is 1. So on one side, sigma x value is 0 and on other side it is 1. And gradient of sigmoidal function is given by sigma x into 1 minus sigma x. So what would the gradient be at saturation? So if your sigma x value is 1, gradient value, if we substitute it here, 1 minus sigma x, if sigma x is 1, 1 minus 1 is 0, and we get gradient value as 0, right? So when your net output is very large, we get gradient value as 0. And when gradient value becomes 0, there won't be any weight updation. Okay. So why would the gradient be, what would be the gradient at saturation? So when your neuron saturates, gradient value is 0, or we can say gradient vanishes. Okay. So now why neurons get saturated? Okay. So if neuron is saturated, gradient becomes 0 and there won't be any weight updation. But what is the reason for neuron saturation? So your sigmoidal function is not 0 centered. So either all the gradients at a layer are positive or all of them are negative. And your del W is always proportional to gradient multiplied by output of sigmoid, which is always positive. So this restricts the possible weight uptake direction. And sigmoidal function is also computationally very expensive. Okay, so because your output of sigmoid, if it is very large, your gradient will be very small or your neuron will be saturated. Okay, so instead of sigmoid, we can go for Banach function. Banach function is centered at 0, but still your derivative for Banach function is 1 minus tan square x. So if your output is 1, your derivative, even for Banach function, there is possibility that derivative becomes 0 or gradient vanishes. Also, Banach function is computationally very expensive because if you look at the equation, it is e raised to x minus e raised to minus x divided by e raised to x plus e raised to minus x. So Banach function is also very computationally expensive. And when we talk about deep neural networks, there are multiple layers. So as compared to conventional networks, you need large number of computations. Okay. So even with Banach function, we can come across vanishing gradient problem, and computationally it is also very expensive. So we can think of some other functions. So as shown here, your vanishing gradient problem can be solved by a function known as rectified linear unit, or short form for this is ReLU. RE stands for rectified and linear unit, that is LU. It is named as ReLU. So this does not saturate in the positive region. So if you look at this ReLU function, it increases linearly with the input, and when your input is negative, you get the output as 0. So as there is linear relationship, your computational load is very less. Actually, you don't need any computation. You simply need a comparison. If your input is greater than 0, output is same as input. And when it is less than 0, output is 0. So max of 0 and x. So we need to simply apply this function max on the net output, and simply this operation gives us the final output. So this is computationally very efficient, and there is no saturation on positive region. So probability of vanishing gradient is reduced by making use of this ReLU activation function. Okay. So in practice, it converges much faster than sigmoidal or Banach function. And if we look at derivative, what is derivative of ReLU function? It is 0 if x is less than 0, and it is 1 if x is greater than 0, because the slope is constant. It is 1. That's why derivative of ReLU function is 1 if your x is greater than 0. So if at some point in a network, a large gradient causes the bias B to be updated to a large negative value, in that case, we can come across dead neuron, because when output is large negative, your ReLU function gives you output 0, and the weights W1, W2, and B will not get updated in back propagation. So in practice, a large fraction of ReLU units can die if learning rate is set too high. So when your learning rate is very high, there is possibility that your output gives you negative output, and when output is negative, ReLU function gives you 0 output, and in this case gradient value will be 0, and again there will be problem of vanishing gradient. So we can, instead of ReLU, we can go for one more option, that is leaky ReLU. So instead of exact 0, we can have some small negative value as output. So here there won't be any saturation even on negative side, because it always give you some output. So this point, if this value is 0.01x, it ensures that at least a small gradient will flow through the network, and even for the layers which are nearer to input layer, there won't be vanishing gradient problem. Again, as compared to sigmoidal or Danish function, this leaky ReLU function is computationally efficient, and it is also close to centered output, because on positive side you are getting some output, on negative side you are having some output. So it is not exactly centered, but it is close to zero centered output. Okay. So this leaky ReLU in general we can write as fx is equal to max of alpha x comma x. Instead of 0.01 we can say it is alpha, and this alpha can be programmable, or alpha is the parameter of the model, and it will be updated during back propagation. Instead of using constant alpha value, we can keep it updating during back propagation iterative process. Okay. So that's all for today's lecture. So your leaky ReLU can avoid gradient or vanishing gradient problem, and that's why with deep neural networks, leaky ReLU is preferred over all other activation functions. So that's all for today's lecture. Please type your attendance in the chat box, your PRN number followed by name, and if you have any doubt, you can